Welcome to Build with Naz. In today's live coding video, we're going to cover tokio-uring, which is actually the implementation of Linux io-uring in Tokio. It's a relatively new crate. It's not that new. In a previous video that I recorded about effective async rest, we went over all the different patterns for using Tokio and async programming, both concurrent and parallel with Rust. And one of the things that I pointed out was that this article that Tokio, when you're trying to do file copy or file operations using Tokio, it ends up being slower than just using the sync version from the standard library and the thread pool. And so essentially, what is this? Why? It comes down to, in that other video in effective async rest, we also implemented a future trait from scratch on a function. And we also implemented a very simplistic executor. And one of the topics we touched upon was wakers and how wakers are tied to system calls in an operating system. So there's something called epoll, which Tokio uses in order to support asynchronous network connections. However, there is no equivalent, like epoll doesn't work with file handles or file operations. And so the general sort of direction has been for file copy, you don't use Tokio, just use the thread pool with the standard library file operations. It even says that in the Tokio documentation, like right here, reading a lot of files. But so you might be seeing what's kind of leading up to what's coming ahead. And that's his tokio-uring crate, which is support for io-uring in Tokio, which it allows underlying asynchronous file I/O operation at the Linux kernel level. So what this means is that not only can network connections be non-blocking, asynchronous, but now file operations can be non-blocking and asynchronous, and that's the beauty of of, uh, Linux io-uring. And we're actually going to go through writing some code in today's video where we use this async non-blocking io-uring kernel support via tokio-uring crate in order to read files and also read and write from sockets, which is going to be really cool. So it actually, this is a pretty old blog post, but here's the crate that we're going to be exploring today. It's tokio-uring, and they have some code example here, but we'll kind of expand on that. And also intermix it with using regular Tokio. So basically create an example where it uses both tokio-uring and quote-unquote regular Tokio in the same main function. So, and I've included all these links in the description of this video, but I just wanted to go through real quick at a very high level. And please read through this material and the associated blog post for this video to get through all these details. I'm not going to spend a lot of time going over what uring is or io-uring is in the Linux kernel, but essentially it's a thing. You need a relatively new Linux kernel for this. I don't know the numbers, but it's 5 point something, I think. And yeah, there's a bunch of content on this that's really good. This is a fantastic website that you should check out to get the deep dive on what it is. But essentially, at a very high level, and then we're going to switch to Rust sooner rather than later because most of this code is written in C or C++. Essentially, the io-uring it allows fully asynchronous I/O operations using as few syscalls as possible. And there's buffers, there's a submission queue, and there's a completion queue. And so you basically create a buffer, hand it over to the kernel, and this buffer lives between kernel and user space. So I think it's very efficient in terms of not copying that data more than once. And in Rust, this looks like you have to allocate a buffer, and then you give it to the you give it to this tokio-uring, and it takes ownership of the buffer, does something, and gives you back the buffer. So there's some interesting semantics with tokio-uring and how it maps to this mental model, but this is roughly what's happening under the hood. And please take a look. There's a lot of really good information in here. about what exactly is happening and why this works. It has everything to do with reduced latency when accessing devices that have really fast access times. So for example, there's this thing called Intel Optane memory, which I don't think they make anymore, but it had very low latencies, like latencies as low as the time it takes to do a context switch in a matter of like microseconds, I think, like 4 or 5 microseconds, something along those lines. So it was really fast. And when using really fast I/O devices, the traditional chunking code up into tasks and then multiplexing them on a set of threads, when a task goes on a thread and then waits and then gets off the thread and then wakes and then is put on a different thread or the same thread, those context switches end up hurting quite a bit. Whereas with io-uring, it's possible to mitigate or not have so many context switches because we're just leveraging the async nature of the underlying syscalls themselves. So there's a whole host of information here on what it is, why it was created, the design choices, and so on. This is also a really good blog post. I'll put a link to this in the description. And this kind of takes the reader through the history of how these syscalls evolved, where, you know, this is your standard issue sync IO, the read and write function, where you allocate a buffer, you call this read or write function on a stream, and then you or read function, and you tell the syscall to fill as much of that buffer as it can, and it tells you how many bytes it's filled. So that's a sync or blocking version. So the async, the non-blocking version looks quite different, and we'll get into the specifics of that. But yeah, check this out. This goes all the way through like how EPOL doesn't work with the file system, access, you know, kind of an overview of what io-uring is, having those two separate queues, the submission queue and the completion queue. And let's see, I think this is more code. And then it goes all the way down to something called eBPF, which we will not be covering, but this is also another very interesting capability in the Linux kernel, which can be used for doing some interesting things related to this realm of this domain. So this one is completely separate. This is a separate approach to not using something like Tokio and just having like dedicated threads which have task queues, and they avoid context switching on that thread because the thread is bound to a CPU core. It's worth checking out. I mean, we're not going to be looking at this. We're looking at tokio-uring, but that's out there. And this article has a lot of interesting information about the io-uring throughput and performance on Intel Optane memory. So very cool stuff. The Optane SSDs. So, which I don't think Intel makes anymore. So with that, the first thing we're going to do is essentially, let's see, where is it? Follow this tutorial kind of roughly to create examples. So here it says gives an example of using the tokio-uring file struct and the tokio-uring start. So this is different than Tokio main. So it's not creating a Tokio runtime as per usual. This is slightly different. And so we can't use the Tokio main macro when using this because there will be a runtime error actually. It doesn't work. The program won't run. So let's do this real quick. Let's make a new crate. We'll call it cargo new, and is it bin? Yeah, sure, why not? Let's just call it tokio-uring, and then new code insiders tokio-uring. All right. And then let me bring this here, make the font bigger so we can see. All right, so the first thing we're going to do here is let's get some imports. So I'm going to actually upload these imports because otherwise it just takes too much time in the video. So there's tokio-uring, this crate that we're bringing in. Where is it? That one. And then we're also bringing in just normal Tokio. Tokio util is for cancellation token, which we'll be using. This is for tracing because it's really nice to see which threads are generating what output when we have a formatted the tracing subscriber, a formatted tracing subscriber, which we'll configure to show thread IDs and thread names, which is really handy. CtrlC because you'll see we'll have like a CtrlC handler that will initiate shutdown because we're going to do a two binaries in this crate. One is going to be a program that just reads from a file and dumps it to standard out. Another is going to be a kind of like an echo server that you can connect a netcat client to, and then you can type something in the netcat client and then you'll see it echoed back. But under the hood it'll be using the tokio-uring. And then we'll also play with how do you in that server, in the netcat server, an echo server, how do you then not only have a tokio-uring runtime but also a regular Tokio runtime, and then how do you have tasks running in both runtimes and coordinating with each other over channels, which is kind of nice. The cross-term crate is just for colorizing standard out like log messages, so it's for better readability. And this terminal async, I think this is for, actually I'm not really sure, but I think we might need this for some other library. Let me see. I think that is needed for, yes, there is a slightly strange behavior when creating a socket server using the tokio-uring structs, where you can actually spawn any number, or you can have essentially some code that you run which binds to a port, and then if that port is bound to already, you can spawn that same code, run that same code again, and it'll bind to that port. But it won't report an error, it'll just take it. So there's a function in Rebel terminal async. There's actually a module to check whether a port is up and running or not, called port availability, that we'll use to check to see if that port is already been bound to essentially error out. And Miet is for fancy error reporting. So let's see. Then actually what we want to do is rename this thing to readfile, because that's the first one we're going to do. And then let's go to cargo toml, and then we'll create some. This is basically, we're going to have multiple binaries in this one crate, so we are just explicitly stating that in the cargo toml. And here we say we're going to do socket server, which I will create in just a moment. And there's socket server, and I think that's pretty much it. So then we can create a new file called socket server, and we can say, yeah, and then something like to do socket server, and here we'll put to do read file. Okay, so that kind of stubs everything out for us to begin. Let's see, yeah. And then, so essentially for read file, let's see. Let's start by importing some dependencies that we would need. So these are the things that we already added in cargo toml. And let us do this. So in here, we're just not going to be using the Tokio or the standard library to read a file. We're just going to be using the tokio-uring variant. And so for that reason, we will need this fs file thing, which is right there. Okay, so let's do fn main. I have meat already in my dependencies, so we can do this. So let's see, what is, oh, and notice we didn't do Tokio main, because this if we did that, this will collide with that. We can try that in a minute. I'll show you what I'm talking about. So here, what we're going to do is we're going to say tokio-uring start, which is the kind of way to do this. And then notice in Copilot it's saying it receives a async block. So instead of that, we're just going to use an async function. So we're going to say read file, and we are going to make, we haven't made this read file function yet. So here this just returns a result, and then let's see, this shouldn't be compiling. That's weird. Let's see what's going on. Okay. Oh, there we go. So socket server, no such. I think I did something sketchy in my imports. Let's see. Can't read source bin socket server. Oh, these are not in the bin directory. Haha. Oops. Should have checked more carefully with Copilot. Okay, now it's saying, oh, of course, it's read file. Wow, one error after another. Read file. Okay, let's do this now. There we go. Now it's working. Okay, good. There we go. All right, so here we're saying, oh, right. It's saying that you got to do this. It's saying that you're not returning anything from this function, and this correctly fails. This works because this basically, if there's an error from start, it'll bail. So now let's implement this read file. So this read file is a future, which means it's an async function. So we can do something like this: async function read file, file name, and we can do like this, path. So essentially that will give us, let's do this, and we're just going to say, okay. Let's see if this runs. Doesn't do anything. And this needs a file name because it says, this expression says that it's essentially using generics and monomorphism. It's saying that give me a type, whatever type you give me as an argument, as long as it implements asref, I'm good. And so we can say cargo toml, which is this ampersand str, which also has a, it basically converts it from this thing to a path, and then there's an asref implementation for path, and that's how this works. It's pretty handy. So let's see if we run this, what happens? Nothing. Exactly. So this is what's supposed to happen. We can say print line something like to do read file using tokio-uring. Okay. And there we go. This is to do it. A lot of times this output is barely readable because of this thing, and then what I'll do is I will, that's why I always tend to import stylize, so I will do this. And then I can say red, well actually I could have done that anyway. Oh, okay, that just reds and bolds the file name, but if I wanted to red and bold the whole message, then what I have to do is unfortunately wrap this thing in a format, and then I have to say, I might be overdoing this. Let's see if this works. We can say toString and blue or something like that. Let's see if that works. No. Oh. And then, oh, that didn't work. Why? So we're saying format this thing. Maybe we just not format this. How's that? Oh. Oops. Actually, that wasn't the problem. It was this. I already had a format. There we go. And there we go. So it basically made it blue and cargo toml is red. So we can also do like, I wonder if we need toString. No, we don't. So we can also say underlined. And let's see how that comes out. So there you go. So it underlined the whole thing. Just little niceties to make it easier to see things in output when there's a lot of log output. So okay, so now we have to implement this this function using the non-blocking async IO with a syscall, a Linux syscall that implements that. So we're not using the standard standard library. We're not also using the Tokio library. So in order to do that, what we need to do is let's make a file, and this file is going to be not the normal file, but it's going to be this file. So to make it more explicit, we can say like this, file open, and then we can just say name. Notice it's async because this is coming from a different place. So actually this one is async, if you will notice, because this is from the tokio-uring crate. So it does a bunch of stuff, and function will return an error if the path doesn't already exist, and that's great. And then so we do await because we're in an async block, and then we can do like that. And then that it doesn't like it because, long story, I'm saying that it returns a miat result. I'm going to do another video on miat error handling next. So this one is saying that convert whatever error comes back from this function into a miat result, which is there's it's easy for miat to take that and do a pretty output using something called a miat report. But so here we do into diagnostics. So that's the thing. You'll see a lot of into diagnostics everywhere. That's what's happening. It's basically taking the error that comes out of this, turning it into one of those, and then returning it so that miat is satisfied. And so that way when an error happens, it'll be bubbled up to the top level. So like when I say run, it goes to do, because it was able to open the file. But if, let's say, we give it a file, like there's a cargo toml file here, right there. So if we had like, let's say we put in a nonsense file name, does not exist. So now we're going to get, that's the miat error. So basically it went to, basically here, we can say not to do, but read file like that. And then when we go to run it, it blows up. So we can also do this from the command line. We can say cargo run. So we can say cargo run bin read file, and then that should blow up the same way. There you go. So it goes read file. And if you don't like all this stuff, we can actually clean up some of these imports. And you can also do -q, which is nice. What is it saying? Unused variable. Oh, okay, we'll deal with that later. So there we go. So read file. That's the file name, which doesn't exist, and this is Tokio error reporting. So again, I'll do a deep dive in this in the next video. Not this video, but a different one that I'm going to post soon. Okay, so now we have a let's add this to my spell checker. So we have this file handle, which is a tokio-uring file handle, not a standard library one or a Tokio library one. Then now is where the paths diverge. So we still need a buffer, but we're going to say buff move, and it's not doesn't need to be mutable because this is going to be passed into um, the readat function we're going to call in a minute. And this you can just put whatever, fix, something like that, or let's do 4096, something like that. Doesn't really matter for the purposes of this experimentation. So here is where things get interesting. So the call we're going to make is file read at, and what we're going to do is we're going to give it the buff move, and we're going to tell it at what position to start reading the file from. So it's going to be 0, and then we're going to wait it. So this is going to return something. So this takes ownership of buff move, and it moves it into this function, and we're just telling it, okay, read from position 0 of the file handle that I've just handed you. So let's see, let's inspect what this returns. So this comes back with a, oh, let's see what the type is. So it comes back with a result containing a usize. So basically a result containing the number of bytes that were read or an error, and followed by the buffer that we just gave it. So let's destructure it. So we can just say this is going to come back with a result, bytes read count, something like that, or byte read count, and yeah, and then the second one is interesting. It's going to be the buff from kernel. It's not really from kernel, from the syscall, but whatever. Essentially, this is, so we move this thing into this function. It hands it off to io-uring, which does its thing. And this buff, it's probably a good idea to read this because I'm probably going to say it wrong, but this buffer, this is the performance optimization with the io-uring where you don't need to double allocate for reads, but there's a really nice explanation of this in here. It's a zero copy system, so that's what's happening here. But yeah, in today's video, I'm not going to do a deep dive of that, but it's more like let's just explore the uring crate and get a handle on that. So I will leave it to you to read this. It's a fascinating read. But and there's also more information here as well, and this one too. Good stuff. Okay, so coming back to our example, where were we? This one. So here, okay, so that's the number of bytes that were read, wrapped in a, that's wrapped in a result, and we have the actual buffer that was moved into this function. It did its thing asynchronously, properly, using io-uring, came back with a buffer from the kernel, let's say, and this is the thing that has the bytes that were read from this file. So let's see. So let's get the actual byte read count, which is going to be, I wonder if we need an, yeah, we do need an into diagnostic. So this gives us the, because we're just unwrapping the error. And then we can just do this. We can say print line. Let's see if this is a read, read this many bytes from file. Let's see if that works. Ah, it would be nice to give it a file that exists. So here we go. Let's run it again. Look at that, read 603 bytes from file. So let's go see what the size of cargo toml is. Look at that, 603 bytes. Okay, so let's just dump that to the output and see what the file contents look like. And the file content should probably not be red. Let's do blue or something. And then let's see what that looks like. Okay, that's unreadable. Let's do green. And then let's see that. Okay, that's terrible. Let's do not underlined. I don't know what this is doing. Why is it doing green and bold here? Ah, Copilot. Okay. So what is this doing? Read this many bytes from file, and it colorized byte count to green, and the rest of it is blue. Okay. So let's do green here, and let's do yellow. Let's see how that looks. Just having a little fun with the output. Okay, that's not that great. Let's get rid of the underlined. Hey, not bad, not bad. So there you go. Read 603 bytes from the file. Read file using tokio-uring cargo toml, and this is the file contents which we saw earlier. That is pretty cool. So this one works as advertised. Woohoo! And then let's see, and we can also run this from the terminal like so. There it is. Excellent. So this is using tokio-uring and actual non-blocking asynchronous file I/O using io-uring. So this is pretty awesome. And I have I'm on Pop! OS 22 something, and so I have a newer Linux kernel. So this is not an issue. I think it's like 5 something. It says in the documentation somewhere, but I'm like it's pretty recent. I mean, it's not that like most modern distros. I think it'll be fine. But in cloud environments, I'm not really sure. Might want to check into that before doing this. And this is on Linux, of course, and I'm running on Pop! OS, which is Ubuntu System 76 makes a Linux version, a distro on top of Ubuntu. So all this works, which is super exciting. Yay! Okay, so now that that's working, let us switch focus to socket server. Actually, I wanted to show one more thing real quick, is that if we put Tokyo main in there and make this an async main function, I wonder what will happen. It will blow up because we are trying to create 2 runtimes, one runtime inside of another runtime. So in this example, the socket server, I will show how to create a Tokio runtime without using this this attribute macro. So let's roll this back. So, but that's an interesting thing to note, that this has to be a regular main function for this to work. So when I run it again, wow, that looks good. Okay, cool. This is very exciting because we now have async non-blocking file I/O. So now we can use tokio-uring fs for reading and writing files. And in Tokyo, if you recall, we weren't able to because, I mean, we could, but it would be slower because it uses EPOL, and EPOL doesn't work with files, but this is io-uring and it does. So this is super exciting. Okay, with that out of the way, the next part of this live coding video is going to be, let's repeat this, but now let's make a socket server, which is essentially an echo server. We should be able to use netcat to connect to it, and then type something on the client side, and it should be echoed. And then we should be able to shut down this socket server by hitting CtrlC. And so I'm going to come up with a very convoluted way to do all of this to demonstrate like how to mingle the Tokio runtime with the tokio-uring runtime. So, because as we saw when we used the attribute macro, that didn't yield any good results. So let's take a look at the socket server next. For the socket server, let's grab some imports to get going. So let's see, we're going to be using these as we build this server program out. So let us stub this thing out real quick. It'll be very similar to readfile, at least for the main function. So let's just copy that, and here we're going to do a tokio-uring start, but instead of readfile, we're going to say start server, and that should get this thing going. Okay. We don't pass a port or anything because this is a made-up example, so we'll just use whatever port is available. But there is a way to get an available port using the Rebel Terminal Async port availability module. So we could do that, but that's a bit overkill for now. We will use this module in just a bit to... this comes from a different crate, actually. This comes from this one. Crate, actually, docs.rs. This is Rebel Terminal Sync. This is a crate that I wrote to make async readline. and async standard out. So here, it's in here somewhere. So basically, that's where this is coming from. But coming back to our socket server, yeah, so we're going to have a start server function, which is also going to be async. Very similar to what we did with the reading the file, and we'll build this up over a few iterations. So we're going to start kind of small. So we do async start server, and that's going to return result. And then what we want to do is the parts that are going to be similar to a regular socket server, like when using Tokio, which we could do, by the way, for this one. But for in this one, we're going to be using tokio-uring runtime with the tokio-uring TcpListener. So so let's do this. We do TcpListener, and here we're going to get, let's say, an address, a socket. Actually, we could do it this way. Sorry, better. Let's say let address socket address, and then what we're going to do is we're going to do whatever 0.0 port 8080. So whatever is on port 8080, we're going to grab that, and let's see, what is it saying? Oh, I see. It's not returning anything. That's what it's saying. So then we're going to do, so in this port availability, there's a function called check, and there's a reason for using this, which is that currently, as this API stands, you can, if you run a process that runs this function and 8080 is available, it'll bind it. If you run it again, it's not available, it'll bind it. So the first process won't be able to access this 8080 anymore. So for that reason, we can do this. We can check to see if the port availability for this address is, let's see, so we're going to say, is it free or occupied? So if it's free, then it's good. We don't have to do anything. We can just say tracing info port is available, and if it is not, then we need to basically break out of this with an error. So we can say tracing error. We can say port is occupied, and then what we can do, instead of doing a standard process exit, which is, there's no need to do that, we can say return error, and what we can say, use met to do something like this, port is occupied. So this will generate a met error. So if there's an error, so let's redo this, so we can do it like this. So this will return, and if all is well, we can just do TcpListener bind, and then we're just gonna connect to the address basically. And this one, we are using the standard socket address here from the standard library. And let's see, tokio-uring, where is this? We're using TcpListener bind address. Why is this not, oh, this is not right. So we can do this here. Okay. So essentially, there we go. And I wonder if, oh, yeah. So basically, we're checking to see, actually, this is fine. So essentially, we have to manually check. since we can bind to the address repeatedly. So here, and then, okay, so if all goes well, we will return a TcpListener. If this port is in use, then it should error out. And then let's see if this runs. So let's do this. Say cargo run, and this one we're gonna do. Actually, let's see what the socket server queue. So let's run that. Okay, so this runs. That's great. Awesome. And since nothing was occupying port 8080, it was fine. So yeah, if we do, like, for example, if we run a different, let's see, serve, let's see. This is a Node.js program that just takes whatever folder and starts a web server. And it serves up the files in that folder. So that should take up a port 3000. So if we now run the same program, actually, and we put 3000, that should error out. So let's see if that works. Yes, there it is. Port is occupied. So this is the error message that we spawned because it's on 3000. But if we kill that server on 3000, run it again, it basically works no problem. Excellent. So this error handling code is functional. That's great news. So now let's actually do something with the server. So we can say tracing info. We can say, actually, there's a bunch of formatting I want, so let me just copy and paste it because it's a bit tedious to create all these formatted strings. So this just goes, okay, tracing info level log. It'll just say, you know, server started. So one thing you might notice is that there's no log output. And the reason for that is that before we can actually see the log output, we have to do one more thing here, and we can say, I guess we could say register tracing subscriber, and here we can just do that. So it doesn't really return anything, just a little utility function basically. And so now we should be able to see, as you can see, there you go, port is available and server started. So that's great. Now let us see. Okay, so now we have to make the sort of the we have a listener, and this behaves very similar to the Tokio variant, or even the standard library variant. That this part is the same. So what we will want to do, let's see, once the server started, we want to, let's see, create an infinite loop where we want to, actually, let's do one thing real quick. What if we want to cancel this server? So here, so let's put a to-do. We can say infinite or main loop to accept connections, or shut down the server. So that's our to-do. So we got to do this. And then this kind of introduces the concept of shutting down the server. So let's just kind of stub this out for a moment. So in order to shut down the server, we're going to use something called a cancellation token. And that is part of Tokio. It's right here. This one. It's in the Tokio util crate. In your previous video for effective async, I had said that to use the broadcast channel, the semantics of which were more favorable to the event loops that I was creating, but in this particular use case, cancellation token is really handy. So we're going to be using this one. So let's do this. So let us make ourselves a cancellation token, which we will actually be passing around to in multiple places. So this is kind of like stubbing out things for the future. So what we can do here is let's create the cancellation token and say let cancellation token equals, yep, there's our cancellation token. And here, let's put another to do. We're going to say in the main function, actually, that's exactly right. We're going to spawn a task to listen for Control-C and cancel the server. And this is going to be using the Tokio runtime. So that's the little twist, is that this is not using the tokio-uring runtime, which is this one. We're going to be intermingling this with the regular Tokio runtime that we're used to. So, but for now, what we're going to do is we're going to take the cancellation token and we are going to clone it and pass it into the start server. So let's do this, cancellation token. Okay, and here now we can kind of flush out the rest of our start the loop, which will either accept a connection and then just basically spawn a task to handle it. And so and for all of this, we're going to be using the tokio-uring runtime, not the Tokio runtime. That's why I'm even doing this, because otherwise the code looks almost exactly like using the Tokio, which is also very similar to what it looks like just using the standard library. So here we're going to see the use of the Tokio select macro. This is again from Tokio, and tokio-uring is compatible with Tokio, so this is really handy. So here we can say, okay, if the cancellation token, if we get a canceled, then we're gonna say, okay, server canceled, and then exit out of the loop. However, if we get, let's see, we can do something like this, where we say, actually, so okay, so let's read through this. So if we get a cancellation token, we're gonna cancel. We're gonna just print a log message, and we're gonna break out of the loop, essentially canceling this thread. So what we can also do is, let's see, so this one, sort of it, what is this? We're getting a TCP, TCP stream. So let's just say we get a TCP stream result. So like that, and then what we can say is that, okay, let TCP stream is that, which is fine. But what exactly is TCP stream? So we just need to destructure this. So we can just say this is TCP stream, and that's we don't need this, but because it's the socket address for on the client side, not the server. The socket address for the client. It's basically whatever port is bound to for the client side of the socket. The server side of the socket is 3000. And so when the netcat client connects, it's whatever port that's coming in on. Okay, so now we can do, let's see, tokio-uring, not Tokio spawn, but tokio-uring spawn. So that's an equivalent. And then here we need to make a handle connection, and let us just do this and just put to do here for now, because we haven't implemented this at all. So, and this TCP stream, as you can see, is coming from tokio-uring. Tokio select is coming from Tokio. Nothing new, but that's kind of cool. So we have like intermingling of the two, which is pretty awesome. So they're from the same family. This is one of the benefits of using tokio-uring. So one thing we might also want to do is that as we are spawning these connections. Maybe what we want to do is save the join handles to them, and essentially when so let's see what this is. The type is, this is a result join error. Yeah, it's just a join handle which contains a result and a report. The report is the miet thing. So into diagnostic, it turns the error into a report and then sends it back. So that's handy. So what we want to do with these join handles is we want to, let's see, let's make a vec called abort handles, which is going to be of type vec abort handle. And what we're going to do here is we are going to put this, let's see, yeah. So we're going to take the abort handle from the join handle and just put it in the abort handles vec. And we are just going to then iterate through the abort handles when the cancellation token is flipped and it is cancelled, and we will essentially abort all the existing TCP connections that might be currently active. So this pretty much takes down the whole server. Okay. So now we can focus our efforts on, that's done actually. So now we can focus our efforts on handling the connection. So this is the actual, like, let's see, this would be, this is, implement the echo server here. So this will be, let's see, let's do this, tracing info. We can just say, why is this so strange? Let's do, actually let's put a stopped here, so we have like a nice balance. Stopped. Okay, so we start the server, we stop the server, and here we can say handle connection start, and this is just asking for OK, and then we can do a handle connection end. Okay. So got server started, stopped, start and end. Okay, excellent. And then the logic goes in here for what we need to do. So let's do this. We need, in order to pull this off, we need a couple of things. Just for reporting purposes, I'm just going to have a counter which records how many bytes were read, and then I'm also going to have a buffer. And the buffer is going to be a buffer of bytes. So 0, and I'm going to make it a tiny little buffer because just for being able to iterate through the loop. Otherwise, we wouldn't even make one iteration of the loop if the buffer was really large. Okay, so the first thing we want to do is we want to we have a TCP stream here, so let's call it stream. And what we want to do is we want to similar to what we did with the file, we have this buffer. We're gonna take that buffer, give ownership of that buffer to the read function this time. So this is how this looks like. So we say stream.read, which is basically this one. Where is it? Something like that. Readet. Stream.read, and then we're gonna do buff, and then we're gonna do await. So then this will return some stuff. So let's see. That is true, because this isn't a loop. The compiler is correct. But this is what we're going to do. We're going to say result num bytes read, because that's the first argument, and the second, or the first item in the tuple, and the second item in the tuple is the buffer that's returned. So we're going to call it return buff. So this is the buff that take a buff, move it in here, it reads a bunch of stuff from the stream, and then generates that buff. And that's a similar situation to this one. Okay. Then what we're going to do is we're going to say buff is return buff. So I'm basically clobbering this thing with whatever the return buff is. So then I am saying let numBytes read equals whatever. So basically now we have, this is again in a loop. So we know how many bytes are read from this read function call to fill this buffer, let's say. That buffer got returned, and then we're taking that return buffer and then assigning to the buff variable. Because remember, it gets moved. So, and then we say check for eoff. So here we can say if numBytes read is 0, we break. That means there's nothing else to read. And this is an echo server. So we can just echo the client back to the, so here we read data from the client, and then we echo the data back to the client. So here we can just say stream write all. And then this is just like, we can grab a chunk of the basically the number of bytes that were read. We slice into the buff, and then we say, okay, from 0 to those many bytes, write it, whatever you've read, just write it back to the client. So then we can do that, and then let's see what we get from the. Okay, so we get another tuple. This one, this is result numBytes written, and then we get the slice that was written. So that's what we get back from this call. So then we can say result. Okay, this is to ensure that there's no errors. So if there's an error, this result will be an error, and this will break and return out of this loop. And then finally, if that works, then we can just say update the buffer. So here we can say buffer equals slice. So whatever slice we got from writing it using write all. We're taking that slice and we're saying, okay, we grab the contents of it, and then we say total bytes read plus, and then we increment this total bytes read just for reporting purposes. And then we can say something like that. So let's see, and then let's see, we can put total bytes read here as well, and that will be and do something like that. Okay. So, and this one, so it's basically the end of the loop. We can just say that, okay, these are the total bytes we've read for the whole time this server's been running, or this, sorry, this handle connection has been handling a client. So yeah, and the loop basically just keeps going until there's either like nothing to read, or end of file. So when it sees end of file, it breaks out of the loop. Otherwise, it just keeps going. It waits for data to become available. The buffer is tiny, So it only reads like 10 bytes at a time, and then does this logic to essentially echo whatever data it read back to the client, and then just goes back on loop and keep going until, yeah. So that's roughly what's going on there. So this is essentially what's happening here. So now that we have this, we should be able to run the server. Let's see. Cargo run. So, okay, server started. And then we should be able to use netcat. Oops. Let's see, what server did we? Oh, should have printed what port. Let's see, port is available. What port is available? Oh, 3000. Okay, so maybe we can say server started, and then maybe report the port in here as well. So maybe we can put something like this, and we can say address that thing. Oh no, that would have to be. Let's see, we only have access to the port in here. Okay, so what we can do is this. Let's do this. And there we go. Okay, so now we can say address. So we'll see like what what port this thing is running on. So it's on 3000. So we can do, actually I thought it was 8080. Let's make it 8080 again. I often have servers running on 3000, so let's just see 8080. Okay, so do 8080, and then here we can say foo bar baz, foo bar baz. So you can see it's printing out how many bytes it's read, and as you can see, it's echoing whatever it's reading back to the client. And when I hit Control-C, that's the end of file, and it essentially goes, okay, handle connection and total bytes is this. And you can see also which thread is reporting, which thread ID, what thread is running this task, which is nice because tracing and tokio-uring, again, Tokyo family, it all works hand in hand, which is really nice. So there we have, instead of using Tokio TCP listener, we're using tokio-uring TCP listener. So that's the difference. It's equivalent to Tokyo. Nothing special here, except that this the functions are a little bit different. Because if you look at the, I mean, this is almost the same. The difference is here, stream.read and stream.write. Actually, no, that's also very similar. I mean, it's the difference is this really, like, it gives you the, in a normal read you would mutate the buffer and fill it, and here, and it would return like how many bytes are read. Here it returns a tuple where the first item is the number of bytes that are read, the result, so this can contain an error, and then that buffer which comes from uring. So so it moves this buffer into here, does the read, and then that ownership comes back to this return buff. So that's the major difference. And then with write all, this is a little bit different too. So because it returns another tuple with the result of how many bytes were written and a slice. So that's the major differences between doing it Tokyo style and tokio-uring style. So now that that's done, the other part of what we can do is, let's see if we can, let's do this. We were going to do this thing, a task to listen for Control-C. Let's do that. So the way that might look like is that we can do CancellationToken clone, and then we'll do this, and then we can say, I have the CtrlC crate, I think, in here somewhere. There it is. So we're going to use the CtrlC crate for this. So we can say, the way this works is you say CtrlC, and then you say set handler, and that's really it. That's pretty cool. So now if I press Control-C, so let's say to diagnostic, and that's gets, because it was returning a result, and to make it MEAT compatible, that's what you have to do most of the time. So here, if we, actually, let's do it here. So here we can do, oops, cargo run socket server. No. Oh, all right. This is in a different folder. Tokio-uring. All right. So let's do this. Let's make the font bigger. Okay. So now we're going to say cargo bin. Boom. That starts the sponsor server. So if I run the server again, it should error out, which is cool. And then, interesting. Wonder why it's saying handle connection start and 0 bytes. That's weird. Haven't seen that before. Interesting. So if we say cargo run bin and then, actually, sorry, if we say netcat localhost 8080, here we say echo, echo, echo. Interesting. Okay, that works. And then Control-C. Let's do this, echo, 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 and then if I see Control-C here, Control-C handler runs, and it stops the server. This is netcat keeps going. I don't think it issued a control D. It didn't send an EOF on that. So this might need some work. Like right now, we just have like a simplistic abort that abort all the things. So that is not that great. I mean, really, there should be like a there should be a way to from the server side to actually disconnect from the basically terminate the connection to the client when Control-C is hit. But you know, this is not, we're not making the most robust server, so this is fine. At the very least, this works. If I do like this, yeah, okay, cool. All right, so let's do this. Let's say that, okay, so that was Control-C handler. But now what if we wanted to use the, this is just made up, but what if we wanted to intermix the use of the tokio-uring runtime with the Tokio runtime? So for that, I'm just going to create a made-up task, a future, which just runs like infinitely, and every 10 milliseconds or so, it just generates a bunch of log output. So it's just kind of meaningless. It's just so that there's a some async, a bunch of async tasks that are running in the background or in the Tokio runtime alongside our tokio-uring runtime. So in order to do that, what we can do is we can say, so this is a bit odd. I'm using standard thread spawn, not Tokio spawn. And what I'm doing is, let's see, is this right? Almost. Almost. So here what we're doing is we're going to do a block on, and this block on is going to do, let's see, worker threads. Just for this example, I'm going to pick a runtime with 4 worker threads built, and instead of that I'm going to say into diagnostic and unwrap. Actually, I can just do this and then block on. Okay. So here, block on, I need to give it a async function. So I'm going to say async fn async main, and I'm going to take a cancellation token. Cancellation token. And we can just put it to here. Okay, so here we can say block on async main cancellation token. Whew. So what this will do, is there an error? Oh. What is this function? Should return a result. Let's see. Or should we just do unwrap for now? Oh, and then this has to be, let's clone the cancellation token yet again, and then here we can say clone. Okay, okay, that's working. Let's see, what is wrong here? Oh, because it's in the spawn. It's this code is actually running in the spawn block, so that's why. Okay, for now we're just gonna say unwrap, which is awful, but that's okay. Here we go. Good enough for now. So actually, if we can also say unwrap and then into diagnostic and unwrap. Yeah, there we go. So let me see. So this will create a new Tokio runtime with 4 worker threads in a new OS thread. So that's the whole Tokio runtime spawning thing. And let's see. So here we have to do that because we can't use the attribute macro, and so here we have something like Tokio runtime. And instead of new current thread, we're going to say new multi-thread, because current thread would end up, that would work too, but current thread is a single thread executor, which is more like concurrent. The task could run in concurrent, but let's just use a multi-threaded executor with 4 worker threads. So there we go. So this is the machinery that has to be set up in order to be able to commingle a Tokio runtime along with a tokio-uring runtime. So what should this async main do? Not much, actually. I'm just gonna, I have this written down somewhere because it's just made up stuff. Basically what it's doing is that I'm going to use an interval which runs every 2.5 seconds, and what it'll do is that it'll just this is in the Tokio runtime. This is in regular Tokio runtime with with actually, yeah, that's right, multi-thread scheduler and 4 worker threads. So here we have, okay, we have an infinite loop, and it goes, it's racing 2 features. One feature is like, are you canceled? If you're canceled, then just say, okay, I'm canceled, and break out of the loop. So basically this won't go on forever, because as soon as I hit Control-C here, and the Control-C handler will flip the cancellation token. It'll basically cancel the cancellation token, and which will result in this branch running, which will result in this loop exiting. Until then, it will just continue running this future. And what it does is that for every tick of the interval, so every 2.5 seconds has passed, it will run all this. And what it does is that it spawns 3 Tokio tasks and then runs them all and then joins their future, so that at the end, these three tasks run every 2.5 seconds, and then it all gets joined, and then their output gets basically once they all finish, this happens, and then the loop can begin again. So what this looks like in practice is when you run it, there's a socket server. Actually, let me clear the screen. So what happens is that, as you can see, it's every 2.5 seconds, it's spawning 3 threads, and I colorized them so you could see like green, red, blue, blue, green, red, blue, red, green. So they're actually happening in different non-deterministic order, which is pretty awesome. So you can track not only the colors but also like what threads they're working that are being used to generate these or to run these tasks, and kind of gives you a sense of how the Tokio runtime is working itself under the hood. And then while that's going, I can still connect to our server, and that works like normal. So we can say echo, 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 and then Control-C out of that, and then when we hit Control-C, that stops everything, ends all the event loops, and exits the program. So there you go. Hopefully this has been a sort of a exploration of tokio-uring, not like fully blown application that works flawlessly. There's a lot of interesting things, like if you run the server twice, then it reports handle connection, so that's something to look at. And also when netcat is running and I kill the server, the netcat instance is still going, so this didn't get a end of file or control D, or its socket didn't get terminated. So these are areas of improvement for this particular program. But yeah, for this particular video, I think this has been an exploration of tokio-uring. So if you like this style of video, please give it a thumbs up. Please subscribe to the channel. That helps a lot, and that way you'll be notified when new content drops. I'm planning to work on a couple of things: Miette, error reporting, clap color customization, and I think one more. I can't remember. I think another video on using state machines for type definitions. There's a word for it, but it's escaping me right now. And then yeah, so those are all coming soon. And also check out Developer Life. I'm gonna create a blog post for this video on Developer Life. If you haven't already, please subscribe, and that way you'll get just notified when new content is dropped. Yeah, hope you enjoyed the video, and I'll see you in the next one.